to Singapore and yes, I got that. To come to Singapore and work with the local universities, the National University of Singapore and the National Technological, the Nanyang Technological University of Singapore. And this attracted a bunch of people, bunch of universities, the MITs, the Yales, Berkeley's there, the Technical University of Munich, Cambridge. Okay. See how that.
Sorry about that.
Let's see.
Something else.
Or like the COVID.
Pandemic for so.
Yeah. Better? Worse? No, it's the online guys. Yeah. Hopefully it's good now. So, anyways, there is this international presence that used to be quite important for development of, or at least that's what was thought, for the development of sciences and advanced technologies in Singapore. But now, 15 years later, the Singapore universities have developed themselves quite a lot, and we enjoy a very equal collaboration with them. And ETH has been present there since the very beginning. First, through this Future Cities Lab, which is an architecture, urban planning laboratory that was concerned mostly with development of such a dense city as Singapore in the face of climate change. And it is hot there. I landed in Berkeley the other day. The coldest it's been in Singapore is 27 centigrade, which is like a little bit less than 90 Fahrenheit. And Berkeley was like 50, and so I froze. But it is a problem that it needs addressing, and that's what it did. And the second center that ETH formed there about 7-8 years ago is this Future Resilient Systems Center. There was a mutual interest in tackling disruptions, cyber ones, also natural ones, even though Singapore doesn't have a lot of those, and of course on the Swiss side too. And this is now where I am. And the newest center that we have there is one that addresses future health problems, digital medicine, personalized medicine, and such. So this is our center, and the Future Resilience program there addresses urbanization and consequences in terms of risk. Because if you think that U.S. cities are dense, well, then you haven't seen Singapore. It is dense square. It is 40-story buildings, very densely packed. The island is probably 50 miles by 25 miles. There is a cross the island trail that's 36 kilometers, so that's a little bit more than 20 miles long. So it is small, and there are about 6 million people living there. Plus, they have lands set aside for water reserve. And, well, okay, a little bit of the military, but the rest of the land where the port is and the industries has been filled. So there is just a lot of exposure there. And the infrastructure demand, you can only imagine. You have to deliver the infrastructure for 6 million people in a very, very small area. So the infrastructure density is also very high. And this makes things very complicated and complex. So here is the downtown. I'll try to just, maybe the mouse is not so visible, but you can see the business district, the old Chinatown, and you can see the supply chain out there, right there. So it is quite dense and quite interesting to see how this whole thing works together. And this is what drew me, and this is what drew a lot of my colleagues to form this Future Resilient Systems program. And right now, the program has 3 parts, 3 clusters. One is on cyber-physical systems. There was a high interest in, from people who basically run power systems and automated systems like trains at the airport, to figure out how to monitor them and to see how reliable they are and how they respond to disruptions. There is the distributed condition and social resilience system cluster, a group of people who kind of come from 2 sides, but they're both looking at the response of people to disruptions, not machines, not cyber systems, not infrastructures. And the cognition part there is about figuring out how people would react, figuring out if there are any weak signals, so both in the machines and the people, to see if there is a disruption coming. And of course, societal social resilience studies how people, how the society in Singapore and overall for Switzerland also responds to not only disruptions but incentives to increase resilience of their communities. And finally, the cluster that I'm in is this high density urban system cluster that I'll talk a little bit more about. So this one is, I'm copied by Professor Edward Law from the US. We are about looking at urban systems as a system of systems. So there is not that many people in there except as users. And the goal is to look at this infrastructure conglomerate, this combination, this integration of infrastructures and the society, this urban housing, and to see how it works together. And one of the important things that we're looking at is the parameter of urban density. How does urban density, especially increase to such an exponential level as it is in Singapore, affect what we think are consequences, what we think are recovery, and does it indeed induce an exponentially longer recovery and exponentially larger effects of disasters? And other people in our cluster deal with energy systems. We are looking at a transition of technology from carbonized one, which Singapore doesn't have nuclear, to more renewables. They do have wind, but not too much, so solar, and also one very important, climate. The urban heat effect is tremendous. The need for cooling is tremendous. That means energy, that means more exhaust. And this interplay between energy cooling and the behavior of people is quite interesting. And then we have a couple of small modules also on financial systems. One is how do people interact with each other, and investors especially, and how we could use that interaction to incentivize some changes of resilience. And the other one is connected to the cyber physical one, in the sense that there is more and more regulation that seems to come from artificial intelligence in terms of how trading is done, in terms of how public policy could be conducted. So that is also interesting. But what I'll talk about is engineering, and what I want to address is this notion of making disaster resilience actionable, meaning what do we need to do to transform an urban system that exists into a more resilient one, and how do we consider actions that need to be done, how do we optimize them and design them that have considering the spatial scale, so going from the state of Singapore down to the particular build neighborhoods, and also over time. We have to focus on near time, and we'll talk about this in the very end, and perhaps mid-decade, 2 decades ahead. But so taking into account some technology change is important, and then we focus on this portfolio of interdependent infrastructure systems, and we have a few case studies. So as an engineer, if we are to design for resilience, I would very much like to see at least a design cycle. One of these things that we are used to with formal design, basically we set out some objectives for this design. These are resilience objectives here. We have a trial design, or if we're designing or redesigning in an existing area, we have this already there, and we've got to evaluate what its state is in terms of disaster resilience, and check if some of the objectives that we set out are satisfied. And if not, then we do improvement. And this is a common way that we design, and it's not easy to make engineers do new things anyway, but it is especially not easy if we wanted to change the paradigm of how they work. So the thing that I want to focus on, there are actually 3 things that I'll talk about today, are first the acceptance criteria. What do we think should these resilience objectives be? And how do we know how happy we are when some of them are satisfying others or not? The second one is the evaluation methods. What do we do to quantify resilience of a community to a disaster, or of a community to many disasters, or of many similar communities to many similar disasters? And how does that part come into this design cycle? And finally, the third thing is the specification of the community. This, when it comes to it, I'll tell you what I think about it, but it involves this statement of the problem in terms of what the community is from the standpoint of resilience and quantification thereof, and what is a disaster, what are the consequences we're looking at, and what is the recovery, how does that process look, and how does it start, how does it initiate, what drives it, when it ends, when does it end. And so let me start with the first topic. So 3 topics, acceptance criteria is the first one. Acceptance criteria, I think we had a lot of discussion about this in the past decade, together with those extremely diverse definitions of resilience, and many papers were written with hundreds of definitions of resilience in them, and I'm sure you read them, and there is the presidential directive, and don't want to go there. But in the end, it turns out that from the quantification standpoint, we mostly agree that the swoosh curve, this up, down, and up curve is what we are going to be looking at. So this is somehow now, nobody says no, as far as I know. I mean, there is a group, I'll mention this, but in most circles that I travel in, this is now quite accepted. And also, there is this the notion of what are the elements, how do we quantify resilience, what could these acceptance criteria be based on? And one are along the horizontal axis, time to recovery. The other ones are along the vertical axis, at some point in time, how much did we drop? It's instantaneous measures. And the third one are cumulative measures. And even there is disagreement. There is like people who measure this gray area here, MCER style. There are people who measure the area under the swoosh. There are people who measure, well, there is all kinds. But there are time-wise measures, there are instantaneous measures, and there are cumulative measures. And again, there are many papers on this. However, in the community that deals with earthquakes, and you'll help me with floods and hurricanes and tornadoes, there's been some process that started with the SPUR project in San Francisco in about the late 2000s, so 2007, 8, 9. They have started to look at issues of housing services, power, water, and they kind of sort of started to plot the axis along the timeline as to how long would they expect the city would be recovering, what would be an acceptable recovery time, and what do they what is going on now in terms of, say, how much time after 9.0, St. Andreas fault nearby, would it take to recover the power, the water, the communication, the housing, and so on. And they set up some very interesting goals. And somehow, at that point in time, I was still in Berkeley, and there was a doctoral student, Mike Miller, who then later on finished at Berkeley Mitrani, and so on and so forth. And I think she's now an Arab. So the question is, if these goals exist, what does it take to design a building to meet them? So 90%, 95% probability of housing shelter 72 hours after the earthquake. And today we know that NIST and FEMA have proposed these kinds of goals. Maybe I should go this way. I don't know. I see your these kinds of functional recovery categories in the new NIST 1254 or FEMA 2090, where they're setting up a matrix that's very similar to what we do in performance-based design for seismic engineering. And there is, of course, hazard levels, and there is the categories of buildings, and what is desirable, base, big spans, and so on. So this I think this fits my picture of how things should go, and I like it a lot. But there is a very large group of people, and this comes out from FRS from Singapore. There was a student, Patrick Gasser, who actually, I was his advisor, then looked at indicator-based resilience metrics. And he proposed a combined indicator for country size indicator that takes into account the electricity, the way that they run it, the number of poles they have, the income of the people, and a whole bunch of measures, and ranks country resilience. And okay, so that's fine, but it may not be as concerning as kind of sort of some of this research. But there is a document from our colleagues who are also working with female homeland security, who really use indicators on a national scale, that are societal indicators and technological indicators to deliver indicator-based resilience objectives. So the objective isn't to fix a pipe, but the objective is to increase the percentage of kids in school, for example, or median income, or health. And how are we going to reconcile the FEMA tables with this? I don't know, but we probably have to talk about it. Because otherwise they're going to branch off and go somewhere, and we're going to go the other way and probably never meet. So this is an issue that I will just skip and go back to the engineering stuff. So the second engineering thing I want to talk about is evaluation of resilience. And here I will go back to a quote from Bob Budbitz. He's a physicist at LBL who worked a lot on nuclear safety. And he was very active in seismic safety and hazard evaluation, and did a lot of reviews for power plants. And basically, Mike Mueller and I and Bob worked together initially. And his statement is that analyzability is a design requirement. So basically, if you want to design something, you better be able to analyze it. Otherwise, your design will be, well, just off the cuff. So this is why evaluation of resilience is extremely important for us. We will not be able to establish the design cycle at all until we have a tool to analyze it. So going back to statics, for example, we can get the same result with the displacement method and the force method. And that's what we test our students on. And if they don't do this, they fail. That's how the exams are. And we've got to be able to do something like this in terms of resilience. People need to be able to analyze in different ways, but come to a consensus, at least to come back to the result. And so, and there are many ways to do this. And there was a paper by Oyang almost 10 years ago now, mostly focused on vulnerability, but he also talks about resilience, and he classified it in 6 categories. And there are, again, not as many papers as there are of resilience definitions, but there are a number of papers on methodological classifications. But what I'll do is just focus on what we do at FRS and what we do at PTH. And there we have 3 groups of approaches. One is empirical, the other is graph-based, and the third one is flow-based. So I'll talk about each one. And so the empirical approaches are basically about creating the mathematical swoosh curve, one way or the other, that that is, at least we expect that kind of behavior of the system, or actual data that we have from disaster and recovery suggests that the systems behave that way. So we have been collecting a lot of these longitudinal studies for hurricanes and tornadoes and earthquakes, with 2 maybe. But the power recovery, the power people, the outage people do this, but on a much shorter time scale. We're talking minutes or hours. And it turns out to be a ton of data. Now, later, I guess I'll share a paper from Nature that has this database. It's a pretty good paper anyway, but they have, well, indeed, it looks like a swoosh. And so one of the things that I liked a lot about the work in FRS is Beatrice's work, Dr. Beatrice Casodana. She finished at FRS and now is a postdoc there. And she developed a set of, well, a gamma function family. These are exponential functions. It blends, she has one or blends two of them that can reproduce a variety of swoosh-like curves. And then there are 3 or 4 parameters that one has to calibrate to match the problem. And then Dr. Nicola Shen, she joined a little bit later. She did this matching. And so here is how the parameters look like for recovery after Sandy. And I will most likely, this presentation share, but what I'll do is probably put together a small piece of a single page with these links, these DOI links, so you guys can find the papers. And so they did statistical analysis of outages, and on the basis of this, calibrated these swoosh curves. And here, the time is in days, and they recover in like a week, which is what we would expect from a large disaster. But there are many, many more outages, and the recovery times are hours, and they can still fit these curves. So the empirical approach is like, fine, let's get the data, let's fit it in. And this is not the only one. For example, Professor Frambopol has a swoosh curve defined by 6 parameters. Each one is a random number. Okay, and then you go play that game, and pretty much that is one group of approaches. So the next one is graph theoretical, and this comes from looking at transportation systems, mainly, but also our water systems that are graph-like. And the attractiveness of this approach is that once you turn the system into a set of those links, there is a lot of theory that can help you. A lot of graph theory that can point to how connectivity, for example, is one of the main measures, how graph connectivity changes with damage to some links. And if you have a recovery driver inside the simulation, you can also see how the recovery is going. And so there is plenty of work. For example, disease spreading has been done this way. A lot of work at FRS. The first 5 years was done by people working with this, and now Dr. Yi Wang she's doing a graph-based model that has vulnerability and recovery, and she uses a measure of resilience that has nothing to do with technique, measure of performance, that is just the size of this largest connected component in the graph and its evolution with damage and recovery. So no numbers, how does this fit with prima this goes? Not clear, but there is a swoosh curve that's generated, and what she's trying to do is to she has a number of damage scenarios and a number of recovery strategies that are also graph-based. For example, the grid recovery, recover the closest one first, the most important one, and so on and so forth. But she wants to create a stress test to automatically, using optimization, design a really bad disaster that still damages, causes a lot of loss of resilience, even though your recovery strategy may be optimal itself. So the idea is to stress test the community that. But we'll see how this goes. This work is ongoing, but it is one of the graph theory-based approaches. But I am most involved in the flow-based approach to resilience quantification. And what I'll talk about is the use of input-output tables. This is work at FRS. Agent-based models. FRS and both one of my former students did this in PhD. And these compositional models that are either process-driven or optimization-driven, that also I have been working with quite a lot, both in PhD and FRS. And the common features are that there is a process, there is a flow, there is a differential equation, basically, that's underlying the evolution of the system from the point of being damaged through the recovery process until that recovery stops. And it looks at constitutive developments, the basic components of the systems, and the system itself. The second characteristic is that we definitely want to have interdependencies taken into account. In Singapore, it's not possible to work otherwise. You cannot isolate the systems. Perhaps somewhere else where it's less dense you could, but interdependencies are critical to evaluating this, how systems recover, especially after larger disasters. And we want to do two things that are kind of specific to the FRS project. One is this spatial scaling up and down, to be able to evaluate the resilience at the level of the country of Singapore and also at the level of a housing block, using the same tools. And the other one is to input this parameter of urban density into the mix and be able to vary it and see how it affects the consequences of the disaster and how it affects recovery, and then how it reflects improvement measures, what needs to be done in a very dense urban environment to enable it to be more resilient. So input-output tables. Here at your center, you have done economic analysis, and it was this computational general. But it does require a lot of data. So these tables are kind of sort of a good compromise between rigor, not too rigorous, and inflexible, difficult to accommodate to a problem, but they are not too bad in terms of computational demands and data demands. They can also, well, we're going to try to scale them and see how that would work. This all comes from the TFS models in the beginning, and there are many static ones where basically this production matrix area is not changing, and then there are dynamic ones where it is changing, and we are trying to use this dynamic model, dynamic input-output modeling, and Dr. Kata is doing just that. He has his goal is to start with input-output tables at the level of Singapore because we have that data. That data exists. ASEAN data, that is the Asian Economic Cooperation Group, exists. So that at the level of Singapore, this picture over here, national level tables are, it is possible to design and this is done. This is what projections of GDP are based on. And then we want to scale down to sub-national to kind of sort of focus on parts of Singapore where, say, industries or housing is, or banking is, and go down to what the Singapore is called the planning area, and try to look at how you could decompose a national input-output table into regional ones and then compose the system back together. So it is an inverse problem. It isn't going to be difficult. But he has made some good steps forward in this direction, and he's also trying to go to the scale of the block, the housing block. And you will see in the next one when we talk about Asian-based how that will affect. So go from the level of the entire country to the parts, the districts of not the districts, but the areas where certain housing or industry is. So this is where the ports and industry are. This is where the center, the main banking area is, this is where the airport is, and so on, to a particular neighborhood. And so he has done quite a bit of work with this, and has managed to look at input-output tables, and then looks at how the elements of that A matrix, the production matrix, change with the disaster and how they recover. And he used recovery functions from Parker and Santos, and has two test cases that are aimed at 2% of interoperability in the input-output table world. Interoperability is what we would call damage and loss of function. And if it's fast recovery, then the recovery, if the components in the sector is recovered quickly, then this is what the system behaves. And if the sectors recover slowly, we have a bigger dip. And this is quite interesting because these people from major communications who look at the electrical power systems are also saying the same thing, and we are also from the compositional side saying the same thing. So it's quite interesting, but his measures of resilience, the vertical axis This in Singapore dollars or in percentages of inoperability, a little bit different than what we are used to. Then agent-based models, this is what Ivo Janowski is working on. These are small automata that are collaborating to put together a system behavior. He has been looking at urban neighborhoods, blocks, and this is an area fairly near to where the Create Center is. It's called Clementi. He divides it into even smaller blocks and associates infrastructure systems. This is a transportation system grid, there is a water one, there is a power one, there is also housing in terms of how many people are there. Let's each one of these agents have a production process. So the agent takes raw materials and produces some water, power, or housing, or supply of information services, and at each node of the system. So each node has a bunch of infrastructures in it. There is a disruption generator that damages the production table, and then there is a recovery process. So it's a small I/O. It's an I/O table in an agent, and that's how we want to link and scale up and down, basically nest one into the other. And interestingly enough, of course, if he gets the disruption and the recovery, and he uses those gamma functions from the agent to simulate the recovery of individual agents, then or when he integrates the entire block, he gets these kinds of swoosh-like curves. This is a small disruption. Only one block of this grid is disrupted, so it's an exponential one. And again, it fits into the mold. But first of all, we can talk about the boundaries of this problem. Very impossible to solve. And also his units. Inoperability is measured in negative Singapore dollars. So the area, if you want to do cumulative measures, the area here is minus Singapore dollar hours. I mean, what do you do with that? So these are this is one aspect of the flow based, and the third one is the compositional one. So this is what I have been working on since I came to ETH about 10 years ago or more, and the goal is to represent the community, to extend the performance-based seismic design approach by looking at a lot of things that the community has. Housing, the power system by its components, the water system by its pumps and pipes, the communication system by its nodes, and if it's wireless, by base stations. And then to simplify the problem, try to cluster this a little bit and create a grid-like, a network, a graph-like structure. But then deploy a supply-demand model in there. So basically, every element of the model has a need for resources and services to function. It has something that it produces, one or more things. And there is not really an I/O table driving it, but there is a production function that depends on the damage of that component. So if the damage exists and then it recovers, then the production rises. But if there are no supplies for that production, nothing is produced. So even though you have a pristine unit, it may still be out of the system. And that is how we capture interdependencies. And the way that we see them is in this gray area here. The difference is the drop. I mean, this is a piecewise swoosh curve because most of the recovery functions in this particular model were delayed linear. So there is this impeding factor time that's very Comerius approach from a while ago. So basically wait a little bit until you start recovering and then you start recovering linearly. Therefore, the curve looks like this. But it's a swoosh curve and there are two of them. And this area here is the difference that occurs because of interdependencies. So it is important to capture interdependencies because otherwise we underestimate. Then we can also debate about why we are calling this the resilience measure and all the way up. Probably a good thing to talk about, but I won't do it right now. So these models turn out to be able to produce measures that are compatible with this table. We can estimate the time of recovery, the percentages of unmet demands, and in terms of quantification, we can come close to what I guess Steve McCabe would want. So this is what was very interesting from the ETH side. But there is a student at FRS, Mr. Hamed Kafesnia, who did the same thing, but he didn't have the driver of recovery like in the IRE codes what Nicola is doing. The driver is just the recovery functions. There is a clock ticking, there is recovery going on, and that's kind of sort of the impetus for the swoosh curve. Ahmed has taken a different approach, and he optimizes the system behavior in every time step for the best possible recovery, for the smallest resilience. So there is no specific recovery schedule. It is whatever the optimization process, the optimization tool gives him. And then for the exact same community, as Nicola analyzed, these are the comparisons of the swoosh curves with and without interdependence. But there are small differences, and I was expecting many more, which is actually encouraging, because if the community specify the same way, different resilience quantification methods, different computations of the recovery process give us similar results. So it's hoped that statics or the displacement force method analogy is possible in this field also. But community specification is a problem. And here are, these are the communities that Nicola has been working on, artificial ones like Centerville one, that has been working on in Zurich, and the same ones are now trying to use different methods to evaluate them in FRS in Singapore. But there are a number of problems that we have to address here. The community as a system of systems has a spatial distribution, connectivity in terms of functions. There are components that are vulnerable and recover and function the way they do, and we have to represent this commonly across different models. There is also the disaster. How do we specify disaster? What is the intensity distribution? And how does it change over time? An earthquake doesn't change much over time unless there are aftershocks, but a flood goes up, the water goes up and goes down, and it's a process. And then there is the recovery process and what drives this process also. And so this is something that I will suggest that we talk about, because just within our own work in Singapore, there are these three different models, the draft one, the other table-based one, the Asian-based one. And their input file is very, very, very different. And of course, the outputs. The outputs turned out to be similar. The swooshes come out, but the units are different, and how we will quantify the units consistently remains an open question. So this to me is something that we ought to be addressing. So let me start with a little bit of a review. So in terms of this, making it actionable and making it a design process, how far are we from getting there? In terms of community specifications, I would like to use as much data as possible from what we have now. The GIS is the census, infrastructure systems. We need to be able to represent the vulnerability, the recovery, and the interdependencies. There needs to be a time scale associated with it, and it has to be neutral to the way we quantify it. So the way we specify must not impede someone else from quantifying the resilience in a different way. And here, I think we have a long way to go. And we need a common way to specify community. And we should probably talk about something like a metadata system, where we would have a preprocessor define this in a common way, and then translate to a quantification system as needed. The resilience quantification systems should be able to reflect on the community properties and the system and the component properties in terms of the robustness, and preparedness, and resourcefulness, and definitely discern the presence of interdependencies. And I hope that the FRS work will result also in being able to discern the density. But I think we also have to remain consistent with space, with the size changes. And most important, we need to produce comparable, if not identically, but at least conceptually comparable resilience methods. And this is where I think we need to do more work, basically verification and validation. There are some very recent papers that you guys have published or are just about to publish on this particular issue that address verification and validation in the traditional way. Here is the data from a serial study. Let's see how close we come. And from what I've seen, it's like 30–40%. Do not know if we should chalk it up to uncertainties or we need to do a little bit more work. But there is another way we could try, and that is to develop a cross-validation system where we would give the same problem to different quantifiers and then see what comes out, perhaps. We talk about this a little bit later as to how we can organize this cross-validation exercise. And finally, acceptance criteria. They have to be independent of the community specification and quantification, and not really related to the size or density, and definitely portable across communities that have different hazards, different concerns, priorities, and different capabilities. I mean, we are talking about Singapore, highly developed country. We are talking about here, when we go to Indonesia, it's not very far, it's a different story. Bangladesh, totally different story. We're not even talking Africa. Luckily, they have more things. So this is something we want to do. And then we haven't achieved a lot, but there is this question about indicator-based models in general in non-engineering quantification that reflect high-level functions, hospitals, education, and general societal well-being. I don't know, life quality index, anyone? But we've got to have perhaps hybrid models that are able to capture this more, or really sit down and see how positional models can do more work is the most. And so this is what I talked about, but I didn't talk about a lot of other things. How we assess what is the current state of the system, and what is the reason that we are setting the resilience objectives. How do we know what that functional class B is? Is it weeks or months or days or weeks? Then the improvement strategies. That is an open question from this talk, but certainly there is a need to figure out what they are, to find out what the priority is in terms of sensitivity of particular components, of resilience to particular components, and to do some optimization. Then after the system is instantiated, there is a need to monitor and maintain with respect to resilience. And here stress testing may be interesting. This big signal that FRS is doing may also be interesting. And then for me, the most interesting term is these long-term processes. Right now, we're talking about months, weeks, year, 2 years, but technology changes over decades. And so societal acceptance and society changes over decades. So if you're talking about making a resilient San Francisco for an earthquake that may happen in 2050, we honestly do not know what kind of transportation system they're going to have. They may have a similar power system, but solar may be dominant, who knows? Water, well, I don't know how fast that will change. Will they build a new Bay Bridge? Probably not. Maybe a tunnel, who knows? But these kinds of things are very difficult to predict. So how do we deal with long-term processes, and how do we deal with the technological changes and also societal perceptions? The societies change over time much faster than we can keep up. So a question of how far should this resilience quantification go is also. So just to conclude, the FRS is there with a certain problem, and a conclusion may be that resilience of urban communities is a priority, and for us engineers making this actionable is needed, and perhaps going in the design cycle is a approach problem. And I hope that with this visit we will identify several areas where we can collaborate between the studies. And before I end, here is a thank you to the doctoral students who work with me in Singapore and ETH, the postdocs, the professors I collaborate with, and the current and past directors of the center. And the reason why I thank them is because I have to stress that it is difficult to work in the Singapore environment, and definitely during Corona, they have both done an enormously good job in keeping the center together and getting it funded and sustaining it over this very difficult time. And here is the end of the talk. Thank you very much to the audience on Zoom, and to you guys here in the room, and do look us up.